Hello everyone and thanks for watching Edupedia World videos. I am Manish Agrawal and today we'll continue with the session of mole concept, and in mole concept today we'll start with empirical formula. Okay, we'll see what it is and how to calculate empirical formula. Alright, so let's start with today's topic. First, empirical formula is nothing but similar to molecular formula but in simplest whole number form. Okay, basically if you remember molecular formula, in molecular formula we might recall that we had subscript after each element. Alright, for example CH4, so it basically means C1H4. Okay, and these subscripts 1 and 4 indicate the exact number of atoms of each element that have combined together to form one molecule of our compound. Okay, that was our molecular formula. So empirical formula are nothing but molecular formula in which we have removed the highest common factor from each element's subscript. Okay, let's see, it will be clear, much more clear in a few minutes. Okay, so empirical formula represents atoms in their simplest whole number ratio. Okay. For example, you have glucose. Glucose molecular formula is C6H12O6. Alright, so here the subscript 6 after carbon represents that one molecule of glucose has exactly 6 number of carbon atoms, and subscript 12 and 6 again represents that number of atoms of hydrogen and oxygen are 12 and 6 respectively in one molecule of glucose. So this was molecular formula. In empirical formula, what I will do is I will take the highest common factor, so 6, 12 and 6. Okay, the highest factor which I can take from all these three numbers, that is 6, 12 and 6 is 6. Alright, I can take 6 common from here, I can take 6 common from here, and I can take 6 common from here. So that will leave me with CH2O. Alright, so if I take 6 common from all of the elements, what's left is C1H2O1. Now there is no other whole number which I can take common from each of the three elements. Okay, so this formula CH2O, now I can say that this formula represents atoms in their simplest whole number ratio, and hence this formula represents empirical formula of glucose. Alright, so what we do to calculate empirical formula, first we write the molecular formula, that is we wrote C6H12O6. Then we see which is the common highest number or highest common factor which we can take from all the elements of those molecules. So we took that factor outside. Okay, it is common in all the three elements, so I can write glucose as C6H12O6, or I can write it as CH2O bracket 6 in the subscript. Alright, it means the same thing. The left hand side represents a more common, okay, more accurate way of writing glucose. The middle section, the middle block represents a simpler, a more crude way of writing the formula for glucose. Okay, you must not get confused with this. This represents glucose itself. Okay, now if I remove this 6, then what's left with me is the empirical formula of glucose. Okay, so now we know what is the difference between empirical and molecular formula. Okay, so basically if you will observe, I can say that this is the empirical formula. Okay, let's call it EF. This is the empirical formula, let's call it EF. And this is the molecular formula, let's call it MF. Okay, so basically EF and MF are nothing but, if I multiply EF with some subscript n, a whole number n, I can get the molecular formula. Okay, in glucose case the subscript n was 6. Alright, so if I multiply empirical formula with a subscript n, I can get the molecular formula. So this is the relation between empirical formula and molecular formula. Alright, you have to remember this. So molecular formula is nothing but empirical formula multiplied with a subscript n. N, where n is a whole number. Okay, where n is a whole number. So n can even be equal to 1. Okay, in fact we should say that it is a natural number because it can never be equal to 0. Alright, so n is a natural number. It can be 1, 2, 3, 10, even 100. But it cannot be in decimal and it cannot be equal to 0 or negative. Okay, let's see some more examples. Say I have benzene. Benzene is what? C6H6. Alright, this is the molecular formula of benzene. Similarly, I have acetylene or ethyne. Okay, you will study these molecules later in your organic chemistry. Okay, so acetylene or ethyne has a molecular formula of C2H2. Benzene has a molecular formula of C6H6. Now from C6H6, what is the highest common factor which I can take out from each of the element? Here it is 6 and here also 6. So I can take out 6 common from both of them. So what will be left with me? CH multiplied with 6. Okay, now to convert this into empirical formula, I can simply remove the 6. Okay, the common 6 I had taken out, I can simply remove it. What is left with me is the empirical formula of benzene. Similarly, for acetylene, the common factor is here 2 and 2. So I can just take out 2. So what will be left? What will be left with me? CH. So this is the empirical formula for acetylene. So if you see, benzene also has an empirical formula of CH and acetylene also has an empirical formula of CH. So unlike molecular formula are unique for a given compound, for a given molecule. Empirical formula are not unique for the compounds. Alright, 2 or more, okay, even 3 or 4 compounds might have same empirical formula. Okay, so this is another difference. Now we know two differences between empirical formula and molecular formula. Okay, first difference is empirical formula represents the simplest whole number ratio of the constituting elements, whereas molecular formula represents exact number of atoms of the constituting elements. Second difference is a compound has a unique molecular formula, but 2 or more compounds can have the same empirical formula. Okay, another difference would be empirical formula can be said to be sort of a subset of molecular formula. Okay, so basically if I have the empirical formula, I can derive the molecular formula given further information. Okay, or if I have molecular formula, I can always derive the empirical formula without any further information. Okay, so let's see how calculations for empirical formula are done, and we'll also see the application of empirical formula. So for calculating empirical formula, let's assume an example. The example says that a compound upon analysis was found to have the following composition by mass. We already know the composition by mass. Okay, we remember what we mean by percentage composition by mass and by moles. We studied it in the last session. So right now we have been given percentage composition by mass. Okay, the compound has 40% of carbon atoms, 6.6% of hydrogen and 53.33% of oxygen by mass. These are mass compositions. So our goal is to calculate the empirical formula and empirical mass of this compound. The procedure is very simple. You always have to follow the same set of steps that I am going to tell you. For all such questions, for all the questions of empirical formula, you have to basically follow the same set of steps. Okay, they might make some changes in the question, okay, might tweak it a little bit, but if you just follow the steps, go through the steps, then you will always arrive at the right answer. So let's see. First you have to formulate a table. Okay, the table will look like this. It will have 5 different columns. The first column will be for elements. Okay, the elements in the compound. In our case, we have 3 different elements: carbon, hydrogen and oxygen. Okay, so these 3 elements have together formed our compound. Okay, the next column is the column for mass percent. Alright, the mass composition that has been given to you. So this is the column to fill our mass composition data into. Alright, so let's see our mass composition data. For carbon it is 40%, for hydrogen it is 6.6% and oxygen 53.33%. Since we have been given percentages, okay, it is always easier. Remember this as a trick. whenever you have been given percentages, it is always easier to assume the total mass to be 100 gram. Okay, let's assume the sample of compound that I have with me is 100 gram. Now since carbon's mass in the compound is 40%, then 40% of 100 gram will be obviously 40 grams. Similarly, hydrogen's mass or hydrogen's percentage in the compound is 6.66%. Hence, the mass of hydrogen in 100 gram compound will be 6.66 gram. And similarly for oxygen, it will be 53.33 gram. So instead of mass percent, what I will assume is that my compound's total weight is 100 gram. So since I have assumed my compound to be of 100 gram weight, I can directly write that mass of carbon with me. Okay, instead of mass percent, I can directly assume that mass of carbon with me is 40 grams. Alright, I can directly assume that mass of carbon with me, just a second. So I can directly write that mass of carbon with me is 40 grams. Alright. Similarly, I can write mass of hydrogen with me is 6.66 gram. And mass of oxygen present with me is 53.33 grams. Okay, I can directly fill up this in form of grams. Now since I have gram, I can easily calculate moles. Okay, if you remember the relation between moles and grams, moles is equal to given mass. Alright, moles is nothing but given mass divided by atomic mass or gram atomic mass. So for carbon, it will be 40 divided by 12. Okay, atomic mass of carbon is 12. So if I divide the given mass by atomic mass, what do I get? Around, if you will calculate this, you will find it is around 3.33. Okay, similarly for hydrogen, what do I have to do? 6.66 divided by 1 is equal to 6.66 moles. So this way I get moles for hydrogen. And similarly for oxygen, 53.33 divided by 16. Okay, 53.33 divided by 16 will give me moles of my oxygen, okay, in this compound. So this again comes out to be around 3.33. okay, if you calculate this, you will find that this again comes out to be 3.33. Why do we do this? Why do we convert them into moles? Because the empirical formula or even the molecular formula represents number of atoms of elements. Okay, if you remember from the previous slide, we had molecular formula of glucose as C6H12O6. Okay, whereas the empirical formula was CH2O. Now this subscripts here. Okay, these subscripts are what we want to find here. Subscripts is implied to be 1. Alright. Similarly here the subscript is implied to be 1. So these subscripts are what we need to calculate over here, and these subscripts represents number of atoms or number of moles of atoms. That is why we converted the mass composition into mass and then mass into moles, because we need to calculate moles of different atoms in order to find the empirical formula. Okay, now next thing about empirical formula was, if you remember, I told you that the empirical formula always represents atoms in their simplest whole number ratio. It means if I have 6, 12, 6, this cannot be empirical formula. This cannot be empirical formula. Alright, this is molecular formula. Why? Because in this the atoms are not represented in their simplest whole number ratio. So to get the simplest whole number ratio, what we do is we simply divide all of the moles, okay, the moles for each of the element with the lowest number of moles. Okay, what I mean is, For carbon I have 3.33 moles, for hydrogen I have 6.66 moles, and for oxygen again I have 3.33 moles. Now take the lowest of these three numbers. The lowest is obviously 3.33. Now divide all the three numbers with the lowest number. Okay, so to get the simplest ratio, here what did we do? In glucose case, we divided all the numbers by 6. So we got the simplest ratio, 1, 2 and 1. So 3.33 is the lowest number. Okay, so I divide all of the digits, okay, all of the moles with the lowest number. So 3.33 divided by 3.33 is 1. 6.66 divided by 3.33 is 2. And again 3.33 divided by 3.33 is equal to 1. So this represents simplest ratio. See, now this column, simplest ratio and whole number ratio. Basically why I have written them? Because you might not get such good numbers every time. Okay, this is the example I selected myself in order to ensure that you can catch up this topic quickly. But in a lot of questions you will find that instead of 1, okay, let's say instead of 1 you might have gotten the number here to be say 1.01. okay, you might have gotten the number to be 1.01. okay, similarly for hydrogen, instead of 2, say I might have gotten the number to be 2.1, and for oxygen instead of 1 I might have got the number to be 1.9. okay, here we have got whole numbers already, 1 to 1, these are whole numbers. So instead of that, if we had decimal, then we need to convert that into whole number. So how do we do that? We either round up. Okay, for example in this case 1.01, it's quite near about to 1, so I can round it up to 1. okay, 2.1 is quite near about to 2, so I can round it up to 2, and 1.9 is again quite near to 2, so I can round it up as 2. So these now 1, 2, 2 represents whole numbers. okay, so in this case I got whole number here itself, but in case I get decimals, then I need to round off. okay, and if I can round off, then I can write the whole number ratio. Now another way of converting simplest ratio to whole number ratio. okay, this example included quite near about numbers. okay, all these numbers 1.01, 2.1 and 1.9 are numbers quite near to whole numbers, so I could directly round off them. okay, what if I cannot round off? For example, the number with me is say 1, 2.5 and say 2. So what do I do in this case? In this case you cannot directly round off 2.5 as either 2 or 3. okay, or say I have 2.6 or 2.7 or even 2.8. okay, you cannot always round off 2.8 or 2.6 to 3. okay, so what do? We multiply all of these numbers by a common factor. okay. Ultimately what these numbers represent? They are ratio. okay, these numbers 6, 12, 6, 1, 2, 1, these are nothing but ratios. So as long as I multiply all these numbers or I divide all these numbers by a common factor, okay, I'm not doing anything wrong, not very wrong with my empirical or molecular formula. So in this case what do? I multiply 1, 2.5 and 2 with a common factor such that all three are converted into a whole number. So 2.5 needs to be multiplied with a number so that it gets converted into whole number. Let's start with 1. Always start with the lowest number. So if I multiply 2.5 with 1, it cannot get converted into whole number. If I multiply 2.5 with 2, it can get converted into a whole number. 2.5 multiplied with 2 is 5. okay, so if I multiply this with 2, I will have to multiply 1 with 2 and 2 with 2 also. okay, I'll have to multiply all three with 2. So when I multiply 1 with 2, do I again get a whole number? Yeah, I got a whole number. Similarly, if I multiply 2.5 with 2, I again get a whole number 5. And if I multiply 2 with 2, I again get a whole number 4. So this time the whole numbers are 2, 5 and 4. So the whole number ratio, this column, the last column, whole number ratio column, would contain 2, 5 and 4 if my simplest ratio were 1, 2.5 and 2. okay, So this is how we convert simplest ratio to whole number ratio. In this case, the example was quite simple, so I can directly write simplest ratio as whole number ratios 1, 2 and 1. Okay, in the next section we'll take up more examples for empirical formula calculation, and in those cases you will see how I convert simplest ratios into whole number ratios. So in this case I finally got whole number ratio. Now these whole number ratios represents nothing other than your subscripts of empirical formula. So the empirical formula for the compound in my question is CH2O. Alright, empirical formula for my compound is C1H2O1. Okay. Now empirical formula by themselves do not have any use. Okay. Their sole purpose is to help us in calculation of molecular formula, especially for unknown compounds. For example, in the above compound, in the question above, in the previous slide, you did not know what the compound is. You were just told that there is a compound which was analyzed in the laboratory, and you found the following mass composition. Now from there you have to estimate which is the compound you are dealing with. Okay. For example, if I have given you a leaf, okay, a leaf from a tree, so you want to find out what that leaf is made up of. So you analyze it in laboratory, you find what are the elements present there, okay, and what is their mass composition. But you cannot see using a microscope what is the molecular formula. You have to estimate molecular formula using this method of empirical formula. So now I have got the empirical formula. From empirical formula I can easily calculate empirical mass. Okay, empirical mass is nothing but similar to molecular mass. Like molecular formula was used to calculate molecular mass, empirical formula is used to calculate empirical mass. So I have empirical formula as CH2O. So empirical mass is nothing but atomic mass of C, alright, atomic mass of C multiplied with, okay, number of atoms of carbon, that is 1, so 12 into 1, plus atomic mass of hydrogen 1 multiplied with number of hydrogen atoms 2, plus 16 into 1, so 30 gram. So this is the empirical mass of this compound. Alright, this is the empirical mass of this compound. Okay, so it's quite similar to molecular mass. Now our ultimate goal is to calculate molecular mass. Okay, sorry, molecular formula. Okay, so now to move on from empirical formula to molecular formula, I need further information. Okay, the question, if from here on we have answered the question, okay, we have calculated empirical formula and we have calculated empirical mass. So this answers our question. But from here on, if we need to move on further towards calculation of molecular formula, we will need more information in the question. Why? Let's see how we can calculate molecular formula from empirical formula. If you remember, molecular formula is nothing but empirical formula multiplied with a subscript n, where n is a natural number. It can be 1, 2, 3, 4 up to infinity. Okay, so molecular formula is nothing but empirical formula multiplied with n. So from here I can directly say that molecular mass is nothing but empirical mass multiplied with n. Okay, it's quite intuitive. Okay, quite intuitive. You can directly see that molecular mass is nothing but empirical mass multiplied with n, where n will be this subscript. So now I have the empirical mass 30. Okay, and I need to calculate n in order to, okay, in order to find my molecular formula, because molecular formula is nothing but empirical formula multiplied with n. So to calculate n, what do I do? N is nothing but molecular mass. Alright, n is nothing but molecular mass divided by empirical mass. N is nothing but molecular mass divided by empirical mass. Okay. So this will answer my question now. Let's say the further information in the question is this, that molecular weight of the compound, in first case it is 30 gram, in second case it is 60 gram, and in the third case it is 180 gram. Okay, there are three different cases now. There are three different questions. The first part of the question was to calculate empirical formula and empirical mass. We have done that. Now the second part is to calculate molecular formula. And for estimation of molecular formula, they have said that there are three different cases. In the first case, it was found that the compound has a molecular mass of 30 gram. So if this is the molecular mass, then I can calculate N. The subscript N was nothing but molecular mass divided by empirical mass. Our empirical mass was also 30. So this gives me N equals to 1. In that case, my molecular formula becomes empirical formula, that is CH2O multiplied with 1, that is CH2O. So empirical formula and molecular formula are same. Okay, in fact this compound CH2O has a structure which looks something like this. Okay, you will study this in your organic chemistry, HCHO. This is called formaldehyde. Okay, you might have heard of this compound. It is used for preservation of biological specimen. Okay, so HCHO, formaldehyde. Okay, if in the second case, if the given molecular mass is 60 gram, then our subscript N is, okay, if you remember again, N was molecular mass divided by empirical mass. So N is, molecular mass is 60 and empirical mass remains the same, 30 gram. So N is equal to 2. In that case, our molecular formula becomes CH2O multiplied with 2. So this gives me C2H4O2. Okay, so in case molecular mass is 60 gram, the molecular formula of compound will be C2H4O2. And in fact, the molecular structure of this compound is something like this: CH3C double bond O OH. Do not get scared by looking at this formula. Okay, these structures you will study them in great detail in your organic chemistry. Okay, I am just giving it here for the reference. This compound is actually called acetic acid. Okay, and it's quite common. You do not realize it, but you use it often in some or other substance in your daily life. So this is acetic acid. So now again 180 gram. Let's say in the last case the molecular mass of the compound is given to be 180 grams. So my N factor here, okay, will be 180 divided by empirical mass, that is 30. This is 6. So in this case my molecular formula becomes empirical formula multiplied by the factor, that is N, that is 6 here. So this becomes C6H12 and O6. This is quite familiar to us now, this compound. By now we have done several examples on this compound. It is nothing but glucose. So you see the same empirical formula might refer to, okay, several different compounds, and in order to calculate or in order to estimate which compound it exactly refers to, we need to have further information like the molecular mass of the compound. In this case, since molecular mass was 30 gram, the compound was found out to be formaldehyde. If it is 180 gram, it was found out to be glucose. Okay, so it might vary. Alright, in the next session we'll take up further examples, 1 or 2 more examples for empirical formula. Okay, they are quite simple. Okay, in fact this might just be the easiest topic in your physical chemistry. Okay, don't get scared if you cannot understand it right now. You just have to follow the steps, okay, and eventually you will get a grasp of it. Okay, and you will realize how easy it is. Okay, so until then, okay, take care, and once again thanks for watching Edupedia World videos.